First speaker of this afternoon's session is Professor Aoyang Zhang from Tsinghua University. Professor Zhang received his Ph.D. degree from Zhejiang University, China, and he got Ph.D. degree from the University of Southern California, Los Angeles. And then he was a postdoctoral fellow at Harvard University, and then he joined Tsinghua University in 2023. He got many awards, very impressive. He got the recipient of USC Best Dissertation Award when he got the PhD degree, right? And then he got the Predoctoral Achievement Award from SSCS, and then he got Best Bachelor Thesis Award from his BS degree thesis. And then the most impressive one is his first prize of Chinese National Mathematical Competition Award. Okay. Yeah, please welcome Professor Zhang for his talk.
Thank you. Thank you. Thank you very much for the kind introduction. So good afternoon, everyone. This is Aoyang Zhang from Tsinghua University. It is my great honor to be here and give a talk. And my talk title is Digital Logic and Hardware Architecture for High Efficiency Computing, from Logic Gates to Domain-Specific Accelerators. First, I'd like to give a brief introduction about me. I received my bachelor degree from Zhejiang University in China, and I pursued my PhD degree from USC in LA. And after that, I did a postdoc at Harvard University, and starting from 2023, and I joined Tsinghua University, and right now I'm an assistant professor. My research experience is mainly in three parts. The first one is digital integrated circuits, and we focused on customized in and near memory domain specific accelerators for many applications, including AI computing, scientific computing, and cryptographic processors. And I will later on introduce what I mean by that. And second part is our group also working on the reconfigurable RF and the mixed signal integrated circuits. And this topic including digital enhanced transmitters, receivers, and leveraging a lot of DSP stuff, and also some front-end modules in RF and millimeter wave circuits to enable high efficiency communications. And thirdly, we recently started building circuits with emergent devices. From my perspective, if you think about a transistor as the bricks, if you're trying to have a building, right, basically, if you change the type of bricks, you may come up with new architecture, and you can have a different type of buildings. So in circuits, I feel it's a similar way. If you change your conventional CMOS transistors into, for example, RRAM, MRAM, even 2D materials, you will be able to leverage some of the properties from these devices and build some cool stuff. So we actually have very recently we built a TRNG plus PUF plus we mapping a security algorithm in a RRAM chip, so you can do computing, can do security, and in IDM. So I really encourage students here to think broadly. So right now, in your generation, different fields actually are emerging. So it's a lot of opportunities if you trying to study different stuff. And today, here's the outline of my talk. I will first introduce the motivation and the background, and also I will talk about the basic first, the number representations. This is essential. I'm sure some of you may already know about it, but I will quickly go through the basic stuff. And then we'll move to core computational units, which is very hot recently because you probably heard a lot of AI computing and Mac and what does it mean, right? And then I will go through the parallel architecture, which is a systolic array, which is a very fashion way to doing computing. And then I will talk the state-of-the-art in-memory computing and some new paradigm. Basically, talk about why we need to use ESA and what's going on right now in the academia. And finally, I will conclude my talk. So first, let's take a look at the motivation and background. As we know, in the 1970s, the Intel 4004 has a transistor count of about 250 transistors. And in 2020, the Apple processor has a transistor count around 100 billion. And this is basically thanks to the, increasing the technology revolution, and we can basically double the transistor size in the past 50 years or 55 years. But now we all know that the Moore's law is slowing down, and it's really hard to increase the transistor density by just using more advanced technology, even though we know that there are a bunch of companies like TSMC, Samsung, and Intel are trying very hard to develop more advanced technology. But we know that it's probably hard to continue going this way. So you can hear a lot of stuff. I'll just hold this. Like, for example, hybrid bonding and trying to make your chip from 2D to 3D, and also some, cool stuff, trying to do a wafer scale computing. And these different methods, basically people are trying to, break this limitation. So this is the overall background I want to talk to you. And let's look at the demand of AI and big data. So we know that in 2018, when the GPT-1 first released, it has a total parameters roughly 117 million. And then for GPT-4, it has roughly 1,800 billion parameters. And last year, the DeepSeek was coming up, and it has a total parameter of 685 billion. They did something in their algorithm so that the active parameter is smaller. But we can see that the modern AI and deep learning models, such as these large language models, indeed demand exponentially increased computational power and to achieve the high performance and accuracy. So from here, we basically ask ourselves, like, what's the solution for such increasing demand of the computing? So there are basically many solutions, and here is a very simple graph to show it. We know CPUs and we know GPUs, and there's another one called domain-specific architectures. I want to basically point out one thing. So if you think about the CPU at the beginning, that was like very hot at the beginning, and later on when the AI is coming up, and we notice that a lot of computing actually can do in parallel. So the GPU is for graphic, and it's naturally suited for this application. But is the GPU the golden state or the golden reference for the computing? I think the answer probably is not. If you think about the traffic, right? So if your traffic is very busy, let's say you have a very high-end car and you can drive very fast. But let's see right now, if the traffic is very busy, even if you have a very high-end car, it may not be the optimal answer for this specific question. Right? Maybe you ride a motorcycle, it will be faster when you travel from A to B because the traffic is busy, and if you ride a car, it's very hard to arrive there on time. Similarly, computing actually have so many different applications. So if you think about it, it may not be a single or a uniform hardware platform to cover everything. If you look at it, NVIDIA, recent product, they actually have different models and different series for different computing power and different ability of problem-solving skill. So we will focus more on the domain-specific architectures, and I will show you a few examples to highlight that why this method is actually very useful and right now is adopted by many industry people. So to begin with, let's first talk about some basic stuff, which is, I think, the most important things in this field, which is the key performance matrix. How to quantify your design by using the TOPS and TOPS per watt. So the equation is showing up here. So TOPS means tera operations per second. So tera means 10 to the power of 12. And to measure the peak computation performance, the TOPS equation is shown up here. So it's basically equals to the number of cores times the Mach unit per core times frequency times 2, divided by 10 to the minus 10 to the power of 12. So the number of cores means the total processing core in your chip, and the Mach unit per core means that in one processing core, how many Mach cells you have. And frequency is basically your operating frequency. And there's also a times 2. And this times 2 means that, because it's a Mach operation, Mach means, M means multiply, and A means accumulation. Basically is multiply and sum. So each Mach operation consists of one multiply and one add. So in total, 2 operations. So this is how we calculate the TOPS. And also, if you want to measure the efficiency, you basically just need to divide by the power, right? So this is TOPS per watt. The equation is listed here. Okay, and let's do a quick calculation together. So if an AI chip has 1,024 Mach units and running at 1 gigahertz, and its power is 10 watt. And basically, first you calculate the operation per cycle. Basically, it's 1 clock cycle, how many operations you can achieve. So we know it's a 1,024 Machs, and each Mach consists of 2 operations. So in total, you have 2,048 operations. And step 2, TOPS basically is operations per cycle times frequency, divided by 10 to the power of 12. So you got 2.048 TOPS. And step 3 is TOPS per watt. It's basically your efficiency. And then you just need to use the TOPS number and divide by the power. So you got a 0.2048 TOPS per watt. Yeah, I'm very happy no one's speaking right now. So it means that probably everybody is catching up this material. So now you know this number, and if you look at the, no matter, A-SSCC or IEEE papers, you can basically check the performance and to quantify, their efficiency and also their computing power. And the second part, let's talk about the number. And this part is also, I guess, many students probably learn from your class. And just do a summary here on basically how to represent a number into a binary, right? So the number is listed here, and basically you can, it's a 2 to the power of n, 2 to the power of n, depends on your, before the binary point or after the binary point. So this is also a quick example. If you have a 47, basically you can do divide by 2, and if it remains 1, and you just write 1, this is a quick math, you can get a 47 into binary representation. And also 0.3 is a very similar way. Instead of divide by 2, you do times by 2, right? So you can, if it's 0, then you put a 0 there. If it's 1, you put 1 here. So you can basically convert a decimal number into a binary number. So this is the way we represent integer number, integer positive number, and a fractional number. So in binary style, and also we can do BCD, right? So the BCD code is also have a different way of presenting a number, like 8421 and 5421. For example, here you can see that the BCD code from 0 to 9 is exactly same as binary coding, right? Like, for example, 9 equals to 1001. The only difference is if you have a number called 395, right? So this one, if you use BCD, the BCD basically separate each number by using this coding. Like the 3 is 0011, and 9 will be 1001, and 5 will be 0101. So, and this is basically the BCD coding for this, decimal number. However, the binary is different there. The binary is basically 395, and you need to calculate the to the 2 to the power of n and to convert it to a binary number. And third one is a Greek code. Greek code is also widely used in our communication systems because each of the binary code only have one bit different. For example, 8 and 9. Let's give another example. 7 to 8, right? So the binary is 0111, and 8 is 1000. From 7 to 1, if you basically switch from 7 to 7 to 8. Each and every bit toggles, right? 0111 to 1000, and this can cause mistake if something was wrong, and the output can be totally different. But the Greek code from 7 to 8 only have 1 bit difference. So, and even you mistakenly calculate 7 to 8, your result is still quite similar to 7, so you won't suffer a large discrepancy. So this is also quite useful, and also an ASC code. And this is something that we will not cover here, but these are the few ways to represent numbers. And so far, we only talk about the positive numbers, and we have to talk about the negative numbers in order to call the foliage. So let's talk about the negative numbers. How do we handle them? There are actually a couple ways to represent negative numbers. The first way is sign and magnitude, and it's very easy to understand. That's we can see here as this example. If you have a positive 5, it's basically just a 0101, and if you do negative 5, you can just change the first sign bit from 0 to 1. 0 represent positive and 1 represent negative. So you have a +5 and -5, right? So this is the good thing is very simple and very intuitive. You basically just remember the first bit is your sign bit, and I'm just gonna switch from 0 to 1. I can represent negative number. But this way indeed have some disadvantages. The first one is that when you have a 5 and -5, if you plus them together, the number you will get is something here. So this is basically incorrect because this is minus 10, right? If you think about it. So the answer is incorrect. So this is the first issue. So you cannot handle addition and subtraction uniformly. The second part is you have 2 zeros. Why? Because if you think the first 1 bit is a sign bit, then these +0 and -0 actually, both of them represent 0. And this can cause problems when you are trying to calculate, right? So this is right now the big issues for this method. Okay, and what else? So the second method is called one's complement. So one's complement is basically we just need to do inverse of the positive numbers. For example, the positive numbers here are still represent the original code, while the negative numbers are represented by the inverted bits with the sign bit unchanged. So like here, 0101 become 1010, and the remaining 4 zeros become 1111. So in this case, if we sum them up, the addition and subtraction operations can be unified. However, you still have the disadvantage, right? Like the 2 zeros still exist. You have 8 zeros and 8 ones. Both of them, unfortunately, represent 0, and this can cause issue because you have 1 0 and you have 2 ways to represent two ways to represent them, and this is not a function, right? So this is the problem for one's complement, but it's better than the previous one, right? Because you solve the add and sub operations together. And then we talk about the two's complement. So the two's complement is another way to represent the negative numbers. Here is the way how to understand this two's complement. The positive numbers are still the same, while the negative numbers are represented by the inverse of them, and then plus 1. So we can basically still use 5 and minus 5 as example. So minus 5, we do the inverse of 5 first. So 5 is 0, 1, 0, 1, and minus 5 will be 1, 0, 1, 0. And the plus 1 will be 1, 0, 1, 1. So 1, 0, 1, 1 plus 1. That's the two's complement. We use this way to represent minus 5. Basically just inverse and plus 1. Why this method is good? So if you look at this, first you can do the add and sub together. Because when you add them up, 5 plus minus 5 equals to what? Equals to 0, right? Equals to 0. So you can see that this is basically 0, right? If you think the first one is overflow, 0, 0, 0, 0 basically represents 0. So the answer is correct. That's all I want to say. And the beauty is there's only one representation of 0, and there's no minus 0 exist. And this is extremely important for computation system. And this is the common standard for modern computers. So we start from the number representations, and once you understand this, you will basically able to build your arithmetic computing platforms. I also want to talk a little bit about very famous story from Intel. So Intel built the floating point unit many years ago, and they earned a lot of money because it's a nice product. And one day, there's one customer who purchased the Intel, hardware, and they noticed that there's a bug in their computing platforms. So, and this error is going to happen every 9 billion per time. So you operate 9 billion times, there's the one time it will pop up. So the computing is wrong. And this is a very, very famous thing. You can Google, you will find it. And he reported this thing to Intel, and Intel double-checked and realized that, oh shoot, this is a real issue. So they recall all their, I couldn't remember, it's the series number of their processor. They record all their processors back, and it's caused a lot of, money was basically ruined. So this is actually a very, very big thing. And in industry, there's a team. Depends on the size of the company. It can be few people to roughly 10 or 20 people as an evaluation team. They basically just like you as a designer, you give me a design, and I don't trust you. I will basically check on myself to test all the cases. So they all from the numbers. So this is something that we need to keep in mind. And here's another example of this two's complement. We can see that if we do 2 to the power of 4, which is 1, 0, 0, 0, subtract 7, which is 0, 1, 1, 1, you got a 1, 0, 0, 1, right? So this example is a little interesting. If you think about, if you don't think about two's complement, just 16 minus 7, you got 9. And 9 will be 1, 0, 0, 1. This is the first way to look at it. And second way is, if you think the first bit is overflow, then you got a 0, 0, 1, 0, 0, 0, basically means 0, right? And 0 minus 7 is basically minus 7, right? So the answer is also correct, right? So if you think the first bit is your overflow. So we can see that this method is, there's no problem for this case. And I also wrote a shortcut method. Later on, if you want to convert any number to this two's complement arithmetic, you can use this to do a quick calculation. And here are also some additional ways. So like, examples. The first one is positive plus positive, and the answer is correct. And it uses two's complement if you do positive plus minus 3, like 4 plus or minus 3, and you get an overflow, and the answer is also correct. And you get a minus 4 plus or minus 3, and you have a 1 overflow, and the remaining is also correct. Is this method perfect?
Yes.
Some people say yes. We'll see. So let's look at this case. If you think about the key is 1, like I show up here, like minus 7 is 1001, right? 7 is 0111, and I do a reverse, and then I plus 1. Minus 2 is basically 1110, and you will get a 10111. Remember, the first one is is basically the overflow bit, and so this number is basically 7 instead of minus 9. So actually the result is incorrect. However, minus 4 plus minus 3 is still correct. So this actually is a problem, because when you basically reach 8, the answer is incorrect. And I will talk about why. If you look at this circle, it's basically how we do the calculation. When you have the, let's see my mouse. When you have minus 7 and minus 2 and then minus 2, you basically do 1 step to minus 8 and then 1 step to cross this boundary, and you will move to plus 7. And this is the problem. So whenever you have overflow, the answer will be wrong. Similarly, if you have a 5 plus 3, you basically jump 3 times, right? So first, second, and 3. You will also cross this boundary, and then your answer will also be incorrect. So please keep in mind that in this method, even though this method is used in, I would say, 99% of computing system, you still need to always, have a flag signal, which is your overflow, to double check the result. And this is also how people do. You have an overflow detection method. You will know that the data is overflowed or not. If it's overflowed, we usually think that, okay, this answer may not be correct, and we can just drop that thing. Okay, I finished the hardest part, because usually the number is hard to, maybe a little bit boring. So let's move to the floating point number format. So the floating point number format is a little bit different than what we just introduced to you guys, because this is basically still a number of a bunch of 0s and 1s, but it has a certain format. The first bit is the sign bit, and second part is basically the exponential part. It's a range of data, right? So if this is 8-bit, it means that you're gonna present the data range 2 to the power of 8. And the last part is called mantissa. It's basically the fractional part. We'll give example. So you can see that FP32, which is floating point 32, and this is basically the format. You can represent the data from 2 to the minus 126 to the power of 128. And the last 23 bits represent the fractional parts. So you can represent very small stuff, like this is a very small number, right? And here is the range. So this is the standard format for FP32. So whenever someone told you it's FP32, it must be 1 side bit, and 8 range bit, and 23 mantissa. So this is the first one. And we also heard about the double the double floating point, right, FP32. And this double long or 64-bit format is basically 1 side bit and 11 exponential bit, and also 52 mantissa bit. So you can see that the range is larger compared to FP32, and more importantly, the resolution is also very important. So there is also other stuff like FP4, FP8, BF16. I'm not sure if our audience may hear about this. what about this? I leave a question here and I will answer it later, but I want people to think about it. Basically, at least FP32 and FP64, they are well defined in IEEE 754. So if you open this standard, you will see everything of these standards. And these are basically used in, I wouldn't say now, but like all the scientific computing, including the early stage of AI computing, we're using this standard to basically do the computing. And then we talk about a little bit about circuits. So the core computing units in digital is adders and multipliers. So for the adder is the fundamental role, and it can basically cover all the different type of computing. For example, subtraction, multiplication, and division. The subtraction is basically adding an active number. And multiply is basically, you can decompose it into a repeat, shift, and adders. It's still using the adders. And division is you can implement through subtractions. And the subtraction need adders. So basically, when you have adders, you can cover pretty much every type of computing method, and you're able to implement your circuit by using just adders. So, which also means that if you can shrink the size and power of your adders, you will be able to have a very efficient and a very high computing power circuitry using these techniques. There are also type of adders. I don't go into details. I just show a very simple one, which is the ripple carry adder. I think people know about it. And instead of this, we also have, for example, carry look-ahead adders and other stuff, and trying to make the adder faster. And also for each full adder and half adder cells, there are a bunch of circuits, right? You can basically use dynamic logic to shrink the size and make it faster. And also multipliers. Multipliers is also very important, especially these days. For AI and machine learning, the matrix calculations will need the multiplier. So the training and the inference of neural networks are almost based on the matrix multiplications and the vector multiplications. And for the signal processing, right, when you do a filtering, like FIR filter, it's basically your signal, if you think about the transfer function, it's a bunch of coefficient times e to the minus 1, minus 2, stuff like that. So it's also multiplication. And also, if you do communication, whereas communication, you have modulation and demodulation. And these operations also need multipliers. And more importantly, in some applications like conventional CPU, GPU, and DSP, the multiplier is a key unit that determines speed, power, consumption, and chip area. Because the multiplier is much bigger than adder. It consists of a bunch of adders, basically. And if you look at the array multiplier, it's actually very, very similar as our elementary school math. The only difference is that right now the number is binary, right? So here's a simple example of A times B, and you will get a result at the bottom. And here's a more general way of array multiplier. You basically calculate B0 times A3, A2, A1, A0, and then B1, B2, B3 in sequence, so that you will get the sum of the results by using this way. If you look at the circuit, it's very, very similar to our, introduction on how we calculate the numbers. You will need a bunch of AND gate array and also adder array. The AND arrays basically generate the partial product. Why the AND is a product? If you think about it, if you have two signals, A and B, and go into an AND gate, right? The basic equation is A dot B, right? If A is 0, B is 0, A times B is basically 0. Same as AND logic. 1, 1 will be 1, 0, 1 will be 0, 1, 0 will be 0. So AND gate is basically a multiplier, if you think about it, unless the only difference is only 1 bit, right? So it generate the partial product. And the adder array is to the accumulation. So when you combine these two, you can have an array multiplier. If you do n times n array multiplier, you will need a n times n number of AND gate and number of n of half adders, and n times n minus n full adders. So here is the example. We do 4 bit times 4 bit, and here's all the hardware architecture show up here. You can do a simple calculation. You will see that these equations are well matched with this architecture. So this structure is a regulator, and the speed is slow and latency is proportional to the square of the number of bits. So for the multiplier, there are many good research working on how to make it faster and make it smaller. For example, Carrie Look had, Wall Street multiplier. You can basically make it faster, but this is a very simple way of implementing the array multiplier. While we talk about the number representations and then suddenly jump to the multiplier and the accumulation circuitry, because these two things are the most important definitions if we think about the computation. So nowadays, if you do AI computation, what you basically need to do is A times B plus C, like the equations here. And A, B, and C can be, each of them can be a matrix. So when you do this, you will need to know, okay, what I'm calculating, what is the number of bits, what is the type of the number that I'm calculating. This is the first thing. The second thing is, when I do the multiplier and the plus, what kind of circuitry that I can choose. So these two things is basically the most important thing. And it consists, and both is A times B plus C, we'll basically call it the MAC, right? The MAC is the multiplier and the plus. So if you can basically build a very efficient MAC, you can basically just extend the MAC cells to an array, and you will be able to calculate a bunch of computing questions. So the last sentence is also important. It's the most basic and the core computing units of modern DSA, especially for AI chips. We think about AI as a specific applications. So this is or a specific domain. So this is also in range of this topic. So the MAC is the dot product operations. If you think about the circuit building blocks, it basically looks like this. So you have A and B comes in, and you do a multiplier, and then the result will basically add with the previous seed, right? So we have a register to save the previous output, and then you sum them up, you get a new seed, which is a new output. So the MAC combines these two calculation types, or these two operations within a single clock cycle, and can improve the processing speed. It also maintains the full precision of intermediate product before final rounding, and then it can significantly reduce the accumulated rounding errors. And once we know this, we can actually look into the computing platforms again. So we know that before the transistors keep going up. However, for no matter CPU or GPU, the single thread performance is kind of saturated, and same as your frequency, right? So before you probably hear that your operation frequency increased from a few hundred megahertz to gigahertz range, but now I think it's kind of fixed to 2 to 3 gigahertz. If you're doing a workstation or server, probably the maximum frequency is roughly 4 to 5 gigahertz, but it's saturated. In my opinion, I think the promising way to achieve optimal performance is through parallel computing, or you custom design the computing cells to push it. Because if you really want to scale up your chip, or you want to use more advanced technology, this is something very hard to push. But if you can come up with new architectures, leveraging these new technologies, you can actually further enhance the performance. And I will later on show a few very beautiful examples, hopefully can trigger some of you for your research and career. Okay, let's talk about the systolic rate, which is the first one. I think it's a very important computing method or a way to accelerate your computing process. So the systolic array is a highly regular parallel computing network composed of a large number of simple processing elements. So this is very, very similar to, well, actually the same as your pipeline architecture, right? Before, if you have a bunch of PE and you basically have a memory and PE interact with each other, and PE is for computing, the memory is for saving the data, and you have on top of that you have a control cell to basically interact these two cells. And if the PE can be separated into a bunch of small ones, and then when the first one is done, and you can take the new data, and the second one you can process the data from the earlier one, so that you can make it faster. And there are different type of these PE arrays, and we can separate to three: one-dimensional, two-dimensional, and multi-dimensional. Depends on the size of your problems. And the features of this is we use the input data multiple times to achieve a high computing through the throughput while consuming less memory bandwidth, and also has a local interconnect, and it's very suitable for large-scale implementation. And there are three types of data flows. And one is called wait stationary, WS, and another one is called input stationary, and last one is called output stationary. It basically depends on which data you want to eat stationary or you want to save in the cells, and I will introduce them one by one. So the first one is output stationary. So for output stationary, you have basically two inputs, A and B, and output will save in the register. And these two inputs, A and B, one is your real input data, and another input signal is your wait signal. So you gave the wait signal and input signal into your computing cells, and they do the calculation and they save the data in the register. So this is pretty straightforward. And if you look into it, it's something like this. You will basically, it's like a train. You just go one by one, right? So first step, we can see that A naught and B naught are sending to the cell, and they calculate A naught times B naught. And then A1, A2, and B1, B2 go inside, and you have the second calculations, and so on and so forth. You will have the output saved in the data. So like, cross rows and columns, and you save the computation result. This is the output stationary. And the wait stationary. So the wait stationary, the hardware actually is same as input stationary. We will use the wait stationary as an example. So for wait stationary, note that you will only have one input, which is your real input, like I show up here, like the numbers show up here. And you save your weight in your process element, okay? And then when the data comes in, you will do the calculation, and the output will basically come out of here, right? So this is the wait stationary. Why wait stationary? Because your weight is just already saved there. It stayed there, right? So this is the wait stationary. If you do input stationary, very similar, right? So you change this W11, W12, W13 to your input data, and then your weight is coming through this system. So you will get the output. So it depends on your input data is weight or is your real input data. You can have input stationary and wait stationary. So these are the three different type of numbers, right? So we know this, and how do we use this, right? So this is a question that I want to point out, and we can later discuss on this. So this is the wait stationary map. You can see that basically the weight is already saved in the array, and I'm just getting the input signal. And one by one, the output is coming out. And the last one, when I finish the calculation, we will basically update the output from the bottom side. So the systolic array, the advantage of this is it's extremely high computing density, and the energy efficiency is actually very good for convolutional and fully connected layers calculation in deep learning. How do we choose among these three, right? So if you do AI inference, you can consider using weight stationary, because in these kind of applications, weight is very important. You don't want to write and read the weight many times. You want to just basically, once it is down, I want to just save the weight in my hardware so that I don't need to basically erase them or rewrite them many times to save power. If you're doing general purpose matrix computation, you can consider output stationary. Basically, you can send your input data and your weight at the same time, and then output will just come out. And when you use input stationary, it's something like if your input data is small, because if your input data is too large, it's kind of, you will need a lot of memory size, a lot of register bank to save the input data. If your input data is small, you don't need that much hardware resources. But your input data weight is actually very large. So the weight is very large. So in this case, you can fix your input data and you keep your weight signal, right? So that, and then calculate. So it really depends on your applications. You should choose your different hardwares. So let's take a look at some applications. The first one is a Google TPU. And this is actually using a 256 by 256 systolic array. And in this case, actually, they can reduce a lot of power from the calculation. And if you look at the hardware of their TPU, the Tensor Core process unit, you can see that each of the interconnect is a systolic array, and it has a low LO bandwidth, which is important for these type of applications. It achieved a large number of MAC units. You can just, like each of the MAC is segmented in this array. And it has an 8-bit fixed point MAC unit and can support 16-bit operations. The second one is the systolic array example is using in NVIDIA GPU. And right now, actually, this is quite used in GPU and in their CUDA cores, in their fifth generation tensor cores, so on and so forth. And if you do a close-in view, we will echo back to the question that I asked you guys before. So the IEEE 754 only lists FP32 and FP64 standard, right? But if you look at the GPU, you will notice that in their first generation, they're using FP16. And then for their second generation, they use int8 and int4. It becomes int. Int is like the conventional one. It doesn't have a mantissa and the exponential part. It's just really the binary that we introduced in the first 5 minutes. And the third one is Empire. They use TF32, BF16. And generation 4, they use FP8. And generation 5, which is Blackwell, the B100, they introduced FP4 and FP6. What I want to mention is FP4, FP8, and BF16, TF32, etc. They are not in the IEEE 754. This is something that either Google defined, they want to use this type of data format to do the computation, or NVIDIA decide, okay, we shouldn't use a standard FP32, we should use FP4 or FP8. Why using them? The answer is actually, like the example that I gave you, you really need to look at the application that you want to do. Like I'm right now traveling. If I know the traffic is very busy, I probably will ride a bicycle or take a motorcycle instead of a very high-end car. So for AI applications, we know that the precision is not that important, right? So you don't really need to have a very precise calculation result. It's not like the scientific calculation. You need a very precise data. It's not like that. We can handle it and we can tolerate that. So, and then if we sacrifice a little bit of the precision and we use IP4 or IP8, you actually can have, using the same hardware resources, you can have a multiple IP8. For example, before you have one IP32, now you have a 4 IP8. So in this case, you can double your computing power. And in these applications, you really don't need a very high computing resolution. And I want to show this is because you can see that even for industry, it takes time for them to learn all of this because it's really application driven. You need to know what you need, and then with that information, you can design your hardware. And also, this come up with our topic, which is domain-specific accelerators. And I believe you can already see that depends on your application, like AI or image or security, you can basically get the data flow, know the data information, and from that information, design your hardware. I know many students, they just have papers. Oh, this guy did this, IP8 or IP16, and let me do a similar way, and maybe have a better performance. I think this is a shortcut. This is not the correct way to do the research. You really need to think about, oh, why I need to do this? Why he want to implement this? And from there, you can see, oh, maybe it is for AI applications. Let me look into the data that AI is using. And then from there, you can get actual information, and you can basically customize your hardware for this specific domain. I'm going to give some examples of the domain-specific accelerators. The first one is the Google Gemini. This is the DAC 2021 past paper. They have a spatial array and implement by using their PEs. And their PE is actually very simple. And it only just something that we just talked before, multiply and sum. One cool thing is they based on their data type. They hybrid these two. They hybrid weight WS and output S, right? So this is the weight stationary and this is the output stationary. So by using this, they can actually have a more efficient way, and they can be configured depending on their applications. And the cost of moving data between the memory and computing units in terms of data and power consumption has become a bottleneck. So this is something that people were trying to solve in the past 10 years, basically trying to break the conventional von Neumann architecture. So how to break this architecture? There's a promising way is process in memory. So this can be done in digital or can be done in analog, and I will give a brief introduction about this as well. So the key point is perform computation directly within the memory cells and break the physical boundaries between computation and storage. And you can eliminate the data movement at the end. So here is the idea. So the last one is the digital Mac, right? So you basically get the data from your memory, like your block RAM, SRAM, your cache, whatever, and then put the data in the Mac unit, and the Mac is basically doing the multiply and sum, or a bunch of calculations. This is the conventional way. And the computing memory is basically, you either make the computing inside the memory or make them very, very close. So in this case, we can see that your logic and memory is together, right? So you can get the data from the memory very fast, and you can even calculate your data from the memory. And similarly, the digital processing in memory is also very similar. You can get your digital Mac and your input signal and put them in the logic unit and do the calculation. And the analog computing memory, there are also a bunch of types. One way is that you integrate your array, like usually it can be RAM or some stuff, and you do the calculation in the memory itself, and then you use the ADC and DAC to get a data output. Let's talk about the analog in-memory computing first. And as we can see, the goal is compute the matrix multiplications, and you have input I and your weight and your output voltage. So the idea is actually very clear. You have a straight input, which is your V1, V2, and V3. And you use the Kirchhoff law to calculate your current. Basically is V times G1. G is the inverse of your resistor. And the sum is basically the current app, right? So the total current is the sum of the three current. So you basically use the Ohm's law and Kirchhoff law to do the calculation. And this can be very fast because it's a physical law, but it can have a noise issue. And second part is you will have to have ADC and DAC overhead because you need to convert to digital bits for the remaining computations. The peripheral circuit is complex. The second part is digital in-memory computing. So here I show one example. I don't show the details, but you can see the circuits here. This is basically a 6T SRAM cell. And you get output directly from the SRAM, and you put this small logic inside this memory cell. And you can calculate your output from the SRAM. And then you don't need to really get data from your SRAM. You can basically calculate in the SRAM, and this can be very sufficient and efficient for sparse attention applications. And it also shows a very good TOPS per watt in both INT8 and INT16. And third one is the another calculation for the AR and VR applications. And you can see right here, they basically have a series multiply and sum integrate together to customize the applications for this NERF neural RF applications. And in addition, they also have the frontiers for high efficiency computation research, such as the chiplet, optical computing, and cryogenic computing. And also, we can use these applications for in-memory computing and new paradigms to enhance our computing power. I will go a bit fast to need another 1-2 minutes to finish this. And then actually, if you want to have a more enhanced computing power, you can either improve your yield and reduce the cost. For these applications, actually, once you do it, you do this heterogeneous integration, means that you have your logic die and do hyperbonding with the memory, and to have a very powerful computing platform, you can actually have a much more higher computing platform and reduce your computing time. And last, if you want to use this domain-specific accelerators in some applications like cryptographic processors, you can also customize it by learning, okay, what I need in this cryptographic processors calculations. Usually the calculation only have a few types, and you don't need to implement the FPGA or the GPU to cover all different type of computing operations. You can only need to design for a couple ones so that you will have a very high efficiency and energy efficiency. So the conclusion, as we can see that the first one is the Moore's law is slowing down, and AI demand are driving the shift to efficiency domain-specific architectures. I think in IEEE 2026, there will be more work come up with. And for tooth complement arithmetic is a modern standard for enabling unified and efficient computation. We learned about the MAC. The MAC unit is a core building block for high-performance deep learning accelerators. And also the systolic arrays, there are 3 different arrays to achieve the massive parallelism for matrix operations. And we introduced the PIM and SIM arrays, and this is right now a hot topic. It can overcome the data movement bottleneck by performing the computation directly within the memory. And we can see that the future efficiency gains will be unlocked by emerging technologies like chiplet, optical, and cryogenic computing. I'd like to thank a few of my students for preparing the slides, and feel free to read them. And if you want to learn more, here's a reference of my talk, and there are more and more coming up with. Thank you very much for your attention. Thanks.
Yeah, thank you, Zhang, for the introduction to the domain-specific accelerators. If you have questions, then please go to the microphone. No questions? Okay, let me ask you one simple question.
Sure.
So you talked about TOPS per watt, right?
Yes.
So I'm curious, you mentioned that when we calculate TOPS for the MEG operation, you said that there are two operations, addition and accumulation, right?
Right.
And multiplication,
Yes,
right?
yes.
So multiplication is much complex than addition, right? Then why do we give the same weight for that operation? I mean, multiply by 2, right?
I see.
Yeah.
You're correct. So in terms of the hardware implementation, the multiplier is much more complicated than adder. So here we more focus on the real applications needed by the real need for the applications. For example, for these applications, they will need 5 add and 5 multipliers. So we basically do a static about this. So instead of separate the multipliers into maybe a bunch of adders to do that. So it's really the application driven. So if the application needs this and the people later on have I feel it's a rule of thumb to just calculate how many adder you need and how many multiplier you need and do this calculation. Yeah, but hardware you're correct. Yeah.
Thank you.
Yeah, thanks.
Okay, if we, okay.
There's a quick follow-up question about this. So,
Yeah.
how about do we deal with the number of bits for those type of operations in counting the teraops? Is it somehow, let's say, you do the 1-bit addition for binary network versus 16-bit floating point addition? It's completely different overhead. But how do you count it as operation?
You mean so for 1-bit and 16-bit, are you talking about the int or floating
In
point?
counting the number of operations, how do you deal with the number of bits?
Oh, number of,
So do you define this one operation as addition regardless of any number of bits, or?
yes. So yes, so like, what we do something is like this. So if you have a 16-bit, let's say, 16-bit FP, you can separate into 4 FP4. And so the input is different. We right now in this calculation we don't encounter with the number of bits, but in real case you will need to check the number of the input and take that into account. So you will see one thing is that people usually report different numbers for different computing. Like I think int 8 or floating point 16. Sometimes they have 2 numbers, and that is for that. Yeah.
Okay, thank you, Professor Zhang. Please thank Professor.
Thank you very much.
Thank you.